Hello guys, this is Prime Concept. We want to consider an important topic in electromagnetism, which is AC circuit. So we want to look at a few things under the AC circuit. Now, under this concept, you'll be learning the difference between AC and DC. You'll be learning the inventors of AC and DC. You'll be learning application of AC and DC, of AC, and then you'll be learning, very importantly, the kind of electricity that is being supplied to you at home and how you can maximize the electricity, the quantity of electricity that is supplied to you by the electricity distribution company in your location. So, very quickly, let's get into the business. Now, AC circuit. Very quickly, we have two names also. When you talk about AC, is a type of electricity or a type of current. So it means we have two types of current based on their pattern of flow. So, and these two types of current are the alternating current and the direct current. The focus of this video is on AC. But very quickly, when you talk about direct current, from the name direct, it's a current that flow in a steady direction. It's a current that maintains one direction over time. So it means that the direction of the current does not change. And that is why we call it direct current. But when you talk about the alternating current is a current that reverses direction with time. So it's a periodic current that changes direction over time. That is alternating current. Now, there was a war known as AC/DC war in electricity earlier on when the concept of AC was developing. There was a war between two inventors. One inventor is Thomas Edison, who actually invented the direct current, right? And he built an empire from this direct current distribution. So a young scientist at that time came to meet him and pitched his idea to Thomas Edison. But because Thomas Edison wanted to grow his empire more, he opposed this idea, and this idea was given by the scientist Nikola Tesla. So over time, when they kept on dragging, over time the AC won the war against DC, and then AC became prevalent. The reason why AC won that war was because of the invention of transformers, which now made the distribution of electricity very cheap, right? So with the invention of transformer, by Faraday's concept of electromagnetic induction, AC became prevalent, even though this currently now the DC is coming to take over again. But that is not the basis of our discussion. So very quickly, let's jump into AC. So like we have mentioned, we said alternating current, AC, is a current that reverses direction with time. So that is to say, it changes direction. It always has maybe a maximum and minimum with time. So it is not steady. That is the alternating current. And if we are to denote this, we can use a wave form to denote the AC alternating current. Now, meanwhile, when we talk about alternating current, it includes voltage. These two things are signals. So when we mention alternating current, it also applies to alternating voltage because both of them are alternating signals, right? So an AC current can be denoted by a waveform. So we have different waveforms that can denote alternating signals. We have the most important to us, the sine waveform, sinusoidal waveform, which is what we're going to consider. We have the triangular waveform, we have the rectangular waveform, we have the sawtooth waveform, and so on. So these are different waveforms that indicate alternating current, but our focus is going to be on sinusoidal. Now, so we want to give the waveform for AC. Waveform for AC. So waveform is simply a diagram that tells you how current changes with time. Remember we said alternating current changes. So the waveform is a diagram that will describe how the current is varying or changing at a particular time. So this is the waveform, sinusoidal waveform. It can be like this. So these are currents, which can also be voltage. And then this is our time axis. This is our time axis. So it means that you can see the current at some point goes up, increases, and then begins to decrease, and then begins to increase. So this is the waveform. So in this particular diagram, the current equation would be given as this, which is equal to I naught sine omega t. So this would be the equation, the current, instantaneous current equation for this. Of course, you know that sinusoidal waveform can also be in this form. So we can also have this as a sinusoidal waveform. We can have this and so on. So if you have it in this case, where this is your current and this is your time, both of them are sinusoidal. The difference is that this is a sine function, while this one is a cosine function. So your current or your voltage also, this would now be cos omega t, or you can say your voltage is going to be V naught cos omega t. So these are how we can represent the alternating currents in their waveform. So this waveform denotes that when you check, you notice that the current increases gradually, and at this particular region it has its maximum or highest value. So the current at this point is what we know as the maximum value, which is what this denotes, the peak value, the maximum value, which is same thing at this point. So I naught and V naught are called peak values, or you call them amplitude values, or you call them maximum values, right? Yes, while I, which is a function of time, these are known as instantaneous values. So these or these are called instantaneous values. Instantaneous values. That is to say, we're going to define them very shortly. So this is one of the things we need to know, and this is the equation that guides the AC signal, the alternating signal. So quickly, we're going to define some terms that we'll be using frequently in our study of AC. So we want to look at terms that are used in the study of AC. Now, one of the terms which we have mentioned already, but you would keep hearing in our study as we progress, one of them is instantaneous value. Number one, instantaneous value. Instantaneous value. Instantaneous value for current and voltage are the values of current and voltage at a particular instant or point in time. So they are functions of time. Instantaneous values of current or voltage are current or voltage given at a specific or particular time. So these are current/voltage values at a given point in time. What does it mean? Say you want to tell what will the current be at 2 seconds. That is instantaneous value of current. What will the current be? Because the current changes with time, right? So 1 second the current is increasing, 2 it keeps increasing, 3 then it starts dropping. So the current changes with time. So you are interested in tracking the current when it is 2 seconds, or tracking the current when it is 5 seconds. So at this particular point in time, the current you are tracking is what we know as the instantaneous value of current. And the instantaneous value of current and voltage are given by this equation. I for current is equal to I naught sine omega t. This is the value or for voltage, same way, which is V naught sine omega t. Like I said, we can also use the cosine, or we can go this way. I equals I naught cos omega t, or V equals V naught cos omega t. So these are the equations for instantaneous values of current. You can see they are functions of time, right? Yes. Then secondly, another term which we have already introduced, but we want to officially mention it, is what we know as peak values. Peak values. Peak values of current and voltage are the highest values of current and voltage that are obtained in a circle of an alternating signal. So these are the highest values of current and voltage obtained in a circle. So these are the highest values you can obtain, which I already showed in that diagram. And the peak values from this equation, the peak values are what you have here. So your I naught, your V naught, this represents peak values, and they are denoted, peak values are denoted by I naught or V naught. Some books might decide to use IM, VM, which simply means maximum current or maximum voltage. These are peak values. Let me give you a quick example that fits exam questions. So you can have something like this. They say I equals, let's say, 3 sine 2 pi ft, find the peak current. And they will give us an equation like this under exam condition and ask us to find or deduce the maximum current for this instantaneous value. So quickly, it's very simple and straightforward. So since we have that I is equal to this, I is equal to 3 sine 2 pi ft, we can compare this to the standard equation which we know as I equals I naught sine omega. Remember, 2 pi ft simply means omega, so I can just say 2 pi ft. So when you compare these two equations, you would quickly see that I naught would represent what? 3. So it means that the value of the peak current is 3 amperes. So these are simple exam questions you would be meeting. So that is how you can find peak value of current. Now the next thing we want to consider, the next term, number 3, is RMS values. RMS value. RMS is a short form for root mean square. So RMS means root mean square. Root mean square. So that is the short for RMS, right? Yes. Now what is RMS value? RMS, it's very simple. Let me use an illustration first to explain this to you. Now say you have 2 footballers, right, in the same team, and one of them is a striker and the other one is a goalkeeper. Now you notice that naturally it is not wise to compare these 2 footballers. Though they are in the same team, you can't compare them and say this one is better than this or this is better than this. If I have to compare these 2 persons, one of the things I will do is I will make that goalkeeper to become a striker, so that while he is striking, I can compare his striking skill to the other striker. So it makes more sense to compare 2 strikers, right? Yeah, so meaning that if I have to compare a striker to a goalkeeper, I would move that goalkeeper to become a striker. That is the same thing that RMS does for us. Remember, we have 2 types of electricity. We have DC and we have AC. Now, if I want to compare two voltages or two currents, say I have two voltages, one of them is DC and one of them is AC, it doesn't make sense to compare both of them because they are not playing the same wing or the same position. So what I would do is that I would convert the AC into DC so that I can now compare it to another DC, right? So if I have to compare an AC to a DC, it means I will first of all convert the AC into DC so that that equivalent value can now be compared to another DC. So the system, when you convert an AC into DC, what you now call that particular DC is RMS value. Do you understand what I've explained? Yeah, I believe it's clear. So what it means is that RMS is the DC equivalent of an AC. That's a short way to explain it. So RMS, this is the DC equivalent of an AC. This is just a short way to say it. I will give another definition. So, but RMS value gives us the DC equivalent of an AC value. Or we can say, I'll just say it, I don't have to write it. We can say that RMS value is that steady current that would produce the same heating effect when allowed. Okay, RMS value is that steady current that will produce the same heating effect as an AC when allowed to flow through the same resistor. Now, say you have a resistor, you allow a DC to flow through that resistor, it generates a certain amount of heat. Now, what will now be the equivalent AC that would flow to generate the same amount of heat? That equivalent that would flow through the same resistor to produce the same amount of heat is what we call the RMS value of that AC. So that is what RMS actually is. I think I've over-explained it. So I think with these explanations, the concepts should be clear to us. So if you really understand what I've explained so far under this, trying to use illustrations just so that you can really get it, drop a comment in the session and tell me you understand what I've explained. Now watch. RMS value of voltage and current has formulas, relationships, which can always be derived, but I won't be deriving here. Now we have RMS current is given by the relationship I naught over root 2. And then we'll also have RMS voltage is given by the relationship V naught over root 2. So these are their relationships, which if I punch this, and this can be written as 1 over root 2 times I naught. These two formulas are the same, so that this can also be written as 1 over root 2 times V naught. So if I go further, I can still say that RMS, now if I start from this first one, what is 1 over root 2? Can you punch this? Yes, punch and confirm. 1 divided by root 2 would actually give us 0.707 approximately, then I naught. So it means this is another way of writing RMS current. Say you don't want to use I naught over root 2, then you can use this, you get the same approximate result. Same way, you'd have that VRMS is going to be 0.707 times V naught, right? So same way. Now the next thing we are going to look at very quickly, which I would use to tie up this video, is power. So that in the next video we'll now continue, so I won't make it too long. So the last term for this video is number 4, which is power. Now what is power? Power is the rate at which energy is consumed, or the rate at which energy is dissipated. Since we are considering AC, this is the rate at which energy is dissipated in a circuit. So this is the rate at which energy is consumed or dissipated. So that is power. And we have 3 relationships for power, like we already know from our DC analysis. So we have 3 formulas for power. And power is given by the equation IRMS. So take note that it is the product of IRMS and VRMS. So this is very important. It's not just IV. Now, in some books, when you're treating AC circuits, you would see just IV. So most people don't want to go through the stress of writing RMS, or what they actually mean is RMS values. Now, same way we can have that P is going to be I RMS square times R. And then also P can also be V squared RMS over what? R. Now you should know, when I was teaching this to my students, some of them were asking, why don't you write RMS for the resistor, right? Or the resistance? Of course, resistance is a constant, so it does not fluctuate, so that we can get an RMS value for it. So it's fixed. So what we talk about RMS is for current and voltage. Now, these same relationships we have gotten, we can write them for peak values. Now, say I want to write them in terms of peak values. So I would have, what is IRMS? IRMS is actually peak current over root 2 times VRMS is what? Peak voltage over root 2. So that when I solve this, I have 1 divided by root 2 times root 2. What will it give us? To give us 2. Then I have I naught V naught. So this is what I have. In terms of peak value, there would always be a constant multiple, which is half, right? Multiplying that product. In terms of RMS, there is no constant multiplying. So if you follow this same process, you'd get a relationship for the other one, which is going to be P equals, okay, let's still do it. In place of IRMS, I'll have 1 over root 2 times what now? I naught, all what? Square, because there's a square, then times R. So that P becomes what? Now, this square would affect this square root. It will cancel this, so it becomes 2. So I'll have 1 over 2 I naught square, because the square would affect I naught, it becomes square, then times R. So without solving, the third one should actually be the same thing. 1 over 2 V naught square over R. So these are relationships we can have for power. These are in terms of peak values, and these ones are in terms of what? RMS values. So I believe that this concept is clear. So I'll be taking one problem to illustrate all what we have learned so far. So let me drop the question and then we'll solve it. A load of resistance 5 ohms is connected to an AC supply of 220 volts. Full stop. Find, number one we want to find is the peak voltage. Number 2 is the RMS current. Number 3 is the peak current. Number 4, the power dissipated. So we want to solve these 3 things. This would summarize what we have learned so far in this video. And we have that a load of resistance 5 ohms. So we were given the resistance of the load R as 5 ohms. And then the supply, the AC supply is 220 volts. So you should know that your supply voltage from your socket is always the RMS value. So our RMS voltage is 220 volts, right? Now, the first question says, we should determine the peak voltage, the peak. So we already know that our peak voltage V naught is going to be VRMS times root 2. I hope you are aware. Yes, VRMS times root 2. So I would have that my peak voltage is going to be this, which is 220 volts times root 2. 220 times root 2. So if I punch this, so let me quickly see. Punch that. 220. So I have 311.17. 311.17 volts. So that is my peak volt. You can see it's high, higher than the RMS. So that is the peak value. Now, RMS, you should also know, RMS can also be called effective value. Now, our second question wants us to get the RMS current, right? Now, this time around, current. Now, we know that VRMS from Ohm's law, the relationship still holds. From Ohm's law, VRMS is going to be IRMS times what? R. So since I want to find current and I know resistance, I can simply say that IRMS is going to be VRMS divided by R. And what is my VRMS? It is 220. What is my R? My R is 5. So that my IRMS becomes 220 divided by 5. So which is 44 amp. 44 amp. So that is my RMS current, right? Yes. Then the next is our peak current. So still doing the same thing. We know that our peak current I naught is going to be IRMS times root 2. Because this is not the only way we can solve. We can still use another way. So I have I naught would then be RMS 44 times root 2. So this would give me This would give me 62, approximately 62.23 amperes. 62.23 amperes. Now, for the sake of exams and those that may want to also learn other ways of doing it, you can still go through the relation that V naught is equal to I naught times R, because this would also be true since resistance is constant. So I would have that I naught can also be given as V naught over R, so that my V naught is gotten as 311.17. Remember, we approximated this, so it should give us an approximate value equal to that. So if you still do this, you get same answer, an approximate result, 311.17. Let me see the approximation. So of course, same approximation. So that is what you have, 62.23 ampere. And the last question says we should find the power dissipated. Now we have a lot of formulas we can use. So very quickly, I can just say that power is going to be IRMS times VRMS. So my current, IRMS current is 44 times my RMS voltage, which is 220. So if I solve this, I would have 44 times 220. So this would give me 9680 watts. Or I can just say, if I divide this value by 1000, I would have 9.68 kilowatts. So any one of them can go. Now, do you think there's another way we can solve and get for this power? Of course, we can still solve differently and get this power. So you can use I squared R. You can use the peak values. You get the same result. So at this point, I'm going to stop the video. In my next video, you need to watch my next video. So if you have not subscribed to my channel, do well to hit the subscribe button, so when I post the next video you'll be notified. I'll be doing a lot in the next video. I'll be analyzing purely resistive circuits. I'll be analyzing purely capacitive circuits. I'll be analyzing purely inductive circuits, and then I'll be analyzing RLC series circuit. Then we'll be using phasor diagram to derive a lot of powerful equations that we'll be using. So thanks for watching my video and always supporting me. So share this video with your friends, 10 of your friends. Tell them this is prime concept. I'll see you in my next video. Thank you.